So today I'm reading a paper called MHSAN, Multi-Head Self-Attention Network for Visual-semantic Embedding. Visual-semantic embedding enables various tasks such as image text retrieval, image captioning, visual question answering. The key to successful visual semantic embedding is to express visual and textual data properly by accounting for their intricate relationship. While previous studies have achieved much advance by encoding the visual and audio text data into the joint space where similar concepts are closely related, they often represent data by a single vector, ignoring presence of multiple important components in an image or text. Thus, in addition to the joint embedding space, we propose a novel multi-head self-attention network to capture various components of visual and textual data by attending to important paths in the data. Our approach achieves the state-of-the-art results in image text retrieval tasks as MS-COCO and Flicker30K datasets. Though the visualization of the attention maps that capture distinct semantic components are at multiple positions in the image and the text, we demonstrate that our method achieves an effective interpretable visual semantic joint space. Alright, so this was produced at Korea Advanced Institute of Science and Technology. So they seem to use this sort of self-attention that was also used in BERT or what was the other sort of GPT-2 as well, and the other ExcelNet and other generators. Okay, and they use as a source both text and the video, and then they try to produce really real internal vectors which are based on self-attention, combined sort of the both components. Okay, let's continue shortly with the interaction, and then I'll try to skip to the most important parts of the paper. Various computer vision applications such as image captioning, visual question answering, and image text retrieval rely on multimodal information from images and natural languages. Visual semantic embedding is to map high-dimensionality represented visual and textual feature in common space where their complex relationship is captured, and it is generally assessed by image-to-text retrieval. The key to visual semantic embedding is how accurately input data from each modality are expressed. One popular approach for learning and visual semantic embedding is to employ two-path network, which represents visual and textual data separately using monomodal and encoders. Recent works on two-path networks collapse the visual features into a single vector by fully connected or selective spatial pooling, and the textual features using the last hidden state of the recurrent neural network. However, since image or sentence consists of a set of subcomponents, there can be various descriptions for a single image depending on where the focus is placed within the image, and it is important to propagate information about each component separately when embedding the respective semantics. Previous methods can easily identify the decisive features, but rarely consider relative importance of each feature and complex semantics. Motivated by this observation, we propose multi-head self-attention network for visual semantic embedding that captures the various aspects and components in images and text. Departing from previous methods, our proposed model generates multiple attention weights, focusing on different visual spatial features of the image and semantic features of the sentence in each encoder. Features with a stronger focus are considered more important and have more influence toward the final representation. By explicitly learning on what point in the image and on which word in the sentence to focus from various perspectives, our model provides more abundant information about visual and textual data for joint embedding. In other words, our model encodes important regions and words separately and weights the relative importance between them, which is simply collapsed by selective spatial pooling, or even single attention. Okay. Contribution. Overall, our main contributions are as follows. We propose a new visual semantic embedding network based on a multi-head self-attention module that extracts multiple aspects of semantics in visual and textual data. We demonstrate that our model successfully learns semantically meaningful joint embedding by setting new state-of-the-art record in the image text retrieval on standard benchmark dataset MS-COCO and Flicker30K. From the advantage of interpretability, our own model, we validate the effectiveness of multi-head self-attention and diversity regularization. While the method of generating multiple attention is used in natural language process, to the best of our knowledge, this is the first work that generates multiple self-attention maps for image encoding as well as visual semantic embedding. Okay, related work. Self-attention, let's read this one. Self-attention networks, also called intra-attention networks, are trainable end-to-end, that is simultaneously train feature extraction and attention generation. There have been several approaches to utilizing self-attention to focus on important parts in order to compute a representation of an image, text of data, from motivation to focus on various aspects of data. Several previous works generated attention weights of the same input. Vashwani et al. 25 improved machine translation by attending to multiple positions of encoded features. Sukh-Bhattar et al. Represented the question sentence into continuous vector by generating attention sequentially for question and answering task. Lin et al. And so on and so on. In contrast to previous studies, we propose multi-head self-attention network which generates multiple attention weights that encode the varying localized regions from various perspectives of an image. In our proposed model, self-attention apprehends the various semantics in the image and text for learning visual semantic embedding. Okay, approach. Okay, let's read the approach to understand the figure more. Approach. In order to reflect various semantics of visual and textual data in the joint embedding space, we propose multi-head self-attention module generating multiple attention weights where each weight focuses on the different regions in the image or on different words in the sentence. Basically, the proposed model follows the two-path network that consists of separate image and text encoders, shown in figure 1. We describe the proposed model in 4 components: visual feature extractor, textual feature extractor, multi-head self-attention, and contrastive triplet ranking loss with diversity regularization. So, figure 1. Details of the proposed architecture for learning semantic visual embedding with multi-head self-attention. For each encoder, features of image and sentence are extracted by ResNet and SRU. On the top of the feature extractor, multi-head self-attention network generates attention weight vectors. The final embedding of the image and the text is a two-dimensional matrix. Okay, so let's describe the image a little bit. So on the top left, there's an image which goes through ResNet and one-to-one convolution. We get the image features which are then flattened and passed through some sort of FC layers. Then attention weight vectors are, I guess, extracted and then they are passed for reshaping, for visualization, and as well the attention weight vectors are added to the flattened image features from the previous part, which then forms image embedding matrix. On the on the bottom left, we have a caption for the image, which then is converted via word2vec to, I guess, vectors. And the text is passed SRU. I'm not sure what SRU is. I guess that's some kind of network. And then that is used to extract sentence feature. Then again to FC layers, create attention weight vectors, which are then added with Cartesian product, I guess, to the original sentence features, which together then form sentence embedding matrix, which is, and all at the end, both the image embedding matrix and sentence embedding matrix are formed together, joined, I guess, joined one common joint vector. They call it here joint space. I'm interested in this feature extractor. Before extracting feature of sentence, each sentence is divided into a word unit through the tokenizer, and each word is expressed as a vector representation. Given the sentence S with length n tokens, k-dimensional vector of a ith word in the sentence, and S is a set of word vectors that are independent of each other. Word embedding used for the word representation to extract sentence feature for a layer. Okay, so we use the 4-layer simple recurrent units. Okay, so they use simple recurrent units with dropout. Where I is the hidden state of the SRU. In contrast to other works, we use only the last hidden state H from the neural network as a sentence feature. We use all hidden states as a sentence feature where each represent the context of a word in a sentence. Okay. Visual feature extractor. Similar to 3, we use ResNet 152, pre-trained on ImageNet. Nothing particular interesting here. Okay, multi-head self-attention. We apply self-attention module on the image and text encoder separately to focus on important spatial regions for image representation and words for sentence representation. It contains many minutes of the image and text calculated. Alright, I don't see anything much again this. I will just read the beginning. Moreover, due to the complex relationship between images and text, it is difficult to contain the semantic meanings of the image and the text within the single vector calculated by a single attention weight. To solve this problem, we propose the multi-head self-attention mechanism on the image and the text encoder to capture the diverse aspects of the semantic meaning in the visual and the textual data. Another advantage of multi-head attention architecture in this representation vectors of an image and sentence retain the important information that could be missed on the single attention, which it captures globally important information within the whole image, scene, or sentence. On the top of the feature extractor of each modality, the multi-head self-attention module is applied. Okay, contrastive triplet ranking close with diversity regularization. We basically use triplet ranking loss with hard negative loss T, which has shown significant improvements on image text retrieval task in the previous studies. Since the multi-head attention mechanism can suffer from redundancy problem where each attention vector focuses on very similar region, we use the diverted regularization loss with coefficient lambda employed in 17. Okay, so they use loss total, loss T plus lambda times loss D. Okay, loss T is, I guess they mean here some, is mainly composed, the loss T uses cosine distance between the vectors, but it's a bit more complicated, it can be read from the screen. Minimizing the regularization term with triplet ranking loss, sparse each. Following the hard negative mining strategy, the loss function focuses only on a single contrastive example that has highest similarity score for image and text in the batch, while not similar in meaning. The contrastive triplet ranking goes encouraging the matched embedding pairs to be closer at least margin alpha apart than mismatched embedding pairs in the joint embedding space. Minimizing the regularization term with triplet ranking goes, the matrices M and Q become sparse so that each of the attention vector focuses on different regions. And the word in the encoder. We showed that the effects of diversity regularization in section 4.4. Implementation details, experiment, comparison with state of the art, MS-COCO retrieval task. Okay, table 1. So they have about, they seem to have 1% advantage in most of the scores over other models. Yeah, mostly 1%. Here's an example. A guy that is riding his bike next to train. A man riding a bike past a train traveling along the tracks. A man on a bicycle riding next to a train. Okay. Spatial pool hours. Okay, so the attention here, the red attention seems to be focusing on the train. Comparison of single head self-attention with spatial pooling without attention. Right. Okay, in this subsection we show that the single head self-attention improved the performance of the related task compared to the selective spatial pooling that did not use the attention mechanism. For this experiment we use MS-COCO dataset to see the effects of single head self-attention mechanism at each encoder. We applied the single head attention to each encoder separately. Table 3 shows that our model with single head attention at each encoder slightly improved the performance of image text retrieval task. Visualization. We validate qualitatively why the self-attention performs better than the network using selective spatial pooling through the visualization of self-attention heat maps. On figure 2 we present comparison between self-attention heat map compared to for we observed that the self-attention with single head captures the missing parts of the selective spatial pooling. Again, train contained the description of the image shown on figure 2. Through the visualization, we demonstrated our model is more suitable for visual semantic embedding, where the encoding of the rich details is necessary. Yeah, I guess their picture matches more part of the image which corresponds to the train. Figure 3, an example of image attention heat map, shows the comparison of hours with varying numbers of attention, multi-head, while self-attending with single head, globally collapsing the street, the crowd, and the person riding the bike in one attention map. In the multi-head self-attention, BC show that they are attended to separately in multiple attention maps. Okay, I don't get this exactly. But yeah, I think it's time for conclusion. We present the interpretable and powerful multi-head self-attention network for visual semantic embedding. Different from existing visual semantic embedded models, our proposed network represents the visual and textual data in multiple vectors, generating multiple attention weights where each weight encodes a different part in the data. Furthermore, we enhance the model with diversity regularization loss to address the redundancy problem where the multiple attention mechanism provides similar representations for the data. Experiments on 2 benchmark datasets show that our model outperforms the state-of-the-art visual semantic embedding models by large margin. For the visualization of attention maps, we demonstrate that our proposed method provides various aspects of visual and textual data by encoding semantically distinct parts of the image and the text separately. Notably, our model is able to achieve superior performance with any other resources such as bounding box or image segmentation mask. Since we achieved a significant improvement by applying the multi-head attention module independently in modality encoder, we expect that our model can be widely applied for other computer vision tasks such as image classification, visual question answering, and segmentation. Alright, thanks for listening to this video. I hope you like it. See you next time.